Hello everyone. Today we are going to start initial value problem IVP. If you remember in the last lecture I told you that in the logistic growth model equation we do not have any uh, arbitrary constant because we used an initial condition to solve this model. Okay. Now you would be wondering that how we used this initial condition to eliminate that constant and why we did this, why we eliminated that constant from this solution. So I'll clear all your doubts in this lecture. Okay, so let's start by considering a first order linear differential equation y prime equals to 2x 1 plus y square. Y prime means the derivative of y with respect to the independent variable which is x here. Okay, so it becomes dy by dx equals 2x 1 plus y square. Okay, now we have this differential equation. We can solve this. So we first separate the variables and then we integrate both sides. Now you know that integration of this function will be tan inverse y and integration of this will be x square. And you also know that we add a arbitrary constant while we integrate, right? So now you have tan inverse y equals to x square plus c. If we take tangent function both sides, we'll have y equals to tan x square plus c. Okay, let's say c is a arbitrary constant. Arbitrary constant means we can put any value at its place. Okay, let's try putting some values. So in first case, we put c as 0 and our function becomes y is equals to tan x square. Because c is 0, so it becomes tan x square only. Now when we put c as 5, our function becomes y equals to tan x square plus 5. Okay. Now in case 3, we put c as minus 5 and our function becomes y equals to tan x square minus 5 and so on. Now you can observe that for each value of c, we are getting a unique solution, right? So if we keep putting these values, we'll get infinitely many solutions. Now if you try plotting these solutions on a graph, you will see something like this. This a family of curves. Okay, this is tan x square, this is tan x square minus 7, this is tan x square minus 5, this one is tan x square plus 10, this is tan x square plus 5. So if we keep putting the value of c, we'll find a unique curve for each solution. Okay, so we'll have a family of curves. This family will have infinitely many members, as like we have infinitely many solutions, we'll have infinitely many curves. Okay, now we'll call them one parameter family of curves because each curve is depending on just one parameter, which is c. Now in these many graphs, how will you find out the exact curve which will represent your problem exactly? How will you find out the exact solution out of these many? Now if I provide you a condition that the exact solution that will represent your problem passes through the origin, then you'll find that solution, right, which is tan x square. You can easily observe that which curve is passing through origin. So only tan x square is passing through origin. So that will be our solution. So here you can see that we have infinite number of solutions that we call as one parameter family of curves. Okay, but in some physical applications, we often require a specific solution out of this family, which represents a particular physical phenomena. Okay, so how will we do that using a mathematical perspective? So this was our solution, and we were given the initial condition that when x is 0, our y also 0. That means y is equals to 0 when x is 0, which alternatively means that the curve passes through the point 0, 0. That means origin. So we can put these values of y and x in our solution and we'll find out c. So y is 0, x is also 0. We put x as 0, then y also becomes 0. 0 equals tan 0 plus c. That means 0 equals tan c. And the only value of c for which tan c becomes 0 is c equal to 0. So we got that the value of c is 0 according to this initial condition that we applied. So putting this value of c in our solution, we get y equals tan x square plus 0, which is y equals tan x square. So you can see that how we eliminated this arbitrary constant from our solution just by using this initial condition. Okay, so any problem or any linear differential equation together with an initial condition is known as initial value problem, or you can say that any differential equation together with an initial condition is said to be an initial value problem. Now here we took a linear differential equation, right? But what about a second order differential equation? Here in the first case, it was a first order differential equation, and now we want to know about the second order differential equation. What happens with the second order differential equation? So this is our second order differential equation, and when we solve this, we get a solution yx equals c1 e raised to the power minus 2x plus c2 e raised to the power minus 3x. Now here you can see that in the solution we have two arbitrary constants. In the above one, we had only one arbitrary constant, but in this, because this is a second order differential equation, we'll get two arbitrary constant. Now here we want to find out the value of C1 and C2 both. If we want to eliminate these constants, first we'll find out the values. Okay, now how can we do that? So to find out C1 and C2, it is necessary to specify not only a point through which it passes, but also the slope of the curve at that point. Okay, here we had only one point through which the curve was passing, but here we need two conditions. First, the point through which the curve is passing, and also the slope of that curve at that point. That is y0 equals 0. That means when x is 0, y becomes 0. And also the slope of the curve at x equal to 0. Okay, so for second order differential equation we need two conditions. For first order differential equation we needed one condition. So similarly for nth order equation we will need n conditions to solve it, or we can say to eliminate the arbitrary constant from the solution. Now this is all about initial value problem. We'll start boundary value problem in the next lecture. That's all for today.